Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss the 2019 version of ASHRAE Standard 15, the safety standard for refrigeration systems. We'll start with an introduction to the standard and review the refrigerant safety classifications. Then we'll explain the restrictions on refrigerant use and share several examples for calculating the refrigerant concentration. Finally, we'll overview specific requirements for A2L refrigerants, for machinery rooms, and for refrigerant piping. I know we can't address every aspect of the standard in 1 hour, so I want to also mention that we have a recently revised Trane application manual that goes into more detail on Standard 15 and how to design various types of refrigerating systems to comply with it. To cover this topic today, Trane application engineers John Murphy and Chris Williams are joined by Steve Kujak, Trane's refrigerant technology leader. Chris is currently a member of Standard 15 committee, and Steve is the current chair of ASHRAE Standard 34. So John, can you start us off?
ASHRAE is one of several organizations that write standards for HVAC equipment and systems. These standards are developed following an ANSI process that requires collaboration and public review. It's tedious and time-consuming, but the intended result is a well-researched consensus document. But ASHRAE doesn't have any authority to enforce its standards, so they're written in a way that can be incorporated into building codes. Now, typically, this is a two-step process. First, model code organizations, such as the International Code Council, look to industry standards and other materials for best practices to use as the basis for their model codes. In this case, that's the International Mechanical Code. Then a state or other governing body adopts this model code into law, where it's then able to be enforced by building inspectors. Now, this is important to understand because several years can pass between publication of a standard and its incorporation into a local code. Changes in wording and sometimes intent can even occur along the way. So the bottom line is, when applying Standard 15, be sure to also review the local code. Okay, so let's get into the details of Standard 15, starting with the purpose and scope. As you read these sections, notice that the focus is on safety, even in the name of the standard itself. Therefore, if you ever have difficulty interpreting a particular section, just remember the primary purpose is safety. The rest of Standard 15 details the design and installation requirements for all types of refrigerating systems, from a small window air conditioner to a large water chiller. It applies not only to newly installed systems, but also to replacements or modifications if they change the function or capacity of the system. And it even applies to conversions to a different type of refrigerant. Now, some of the requirements in the standard are general and apply to all system types. Others are specific to the type and use of the refrigerating system. To determine which requirements must be met for a specific project to achieve compliance with Standard 15, the first step is to identify the safety group classification of the refrigerant. Then you determine the occupancy classification of the space that houses the refrigerating system. And finally, you determine the system probability classification. Based on these three pieces of information, you can then identify the relevant safety requirements from the standard. For the first step, Standard 15 references a different companion standard. ASHRAE Standard 34 designates the safety group classification of various refrigerants. And it also provides relevant safety data that Standard 15 uses in its requirements. So Steve is going to spend a few minutes here to explain Standard 34. Steve?
Just a quick introduction of the safety classification system used by Standard 34. Later, we will discuss further details about the safety classification system and how it is used by Standard 15. Historically, refrigerants used in HVAC systems are mostly classified as Group A1, for example, R22, R134A, and R410A. That is, they have a lower toxicity profile and do not propagate a flame in the presence of a strong ignition source. Commonly, Class 1 refrigerants are referred to as non-flammable. Other examples of commonly used refrigerants with alternate safety classifications are 123, which is a B1 refrigerant, and R717, which is ammonia, which is a B2L refrigerant. Hydrocarbons like R290, which is propane, and R600A, which is isobutane, are classified as A3s. These examples demonstrate that other refrigerants other than A1s can be used safely. Many of the new lower GWP refrigerants under consideration are classified A2L, which have a lower toxicity profile with a lower flammability profile. Example of Class 2Ls refrigerants are R32, R1234YF, and R454B. Section 6 of Standard 15 references ASHRAE Standard 34 as the source for this refrigerant safety classification. Standard 34 has two purposes. First, it establishes a system for assigning reference numbers to refrigerants such as R410A. This helps avoid confusion caused by using brand names such as Freon or complications of using the full chemical name or formula. Its second purpose is then to define the safety classifications and the refrigerant concentration limits for all types of refrigerants. Like Standard 15, Standard 34 is under continuous maintenance. Safety data for new refrigerants is added by issuing addenda to the current version and then including those addenda in the following printings of the standard. First, I will cover the toxicity classification system used by Standard 34. In terms of toxicity, the standard divides refrigerants into two classes based on the occupation exposure limit, or the OEL, of the refrigerant. This is the concentration level to which nearly all workers can be exposed to for a normal 8-hour workday and a 40-hour work week without adverse effects. Refrigerants with an OEL equal to 400 parts per million or higher are designated Class A's. Refrigerants with OELs less than 400 parts per million are Class B's. Standard 15 uses toxicity class as one of the ways to define the type of refrigeration system that can be used and the required safety controls. Next, we will discuss the flammability classification system used by Standard 34. The standard classifies the flammability of refrigerants into 4 classes, essentially non-flammable Class 1s or no flame propagation, and then 3 classes to distinguish various degrees of flammability. Historically, most refrigerants used in HVAC applications have been Class 1. In the end, there are non-flammable and flammables. There is a lot of discussion in the industry around the varying degrees of flammability and safety, but what you need to understand is flammables are flammable. Working down from the top, starting with Class 3 refrigerants, hydrocarbons fall into this classification because they have lower flammability limits, LFLs, meaning you don't need much of the refrigerant for it to ignite. They are also easy to ignite and they propagate flames easily. I think most people have experience with igniting hydrocarbons at their homes when cooking. Class 2 refrigerants have lesser flammability characteristics than Class 3s. They have higher LFLs, but are still easy to ignite and propagate flames well. Class 2L refrigerants are characterized by having even higher LFLs, and they are more difficult to ignite. Typically, static electrical discharges will not ignite them, as well as many common electrical outlet discharges. It is important to realize that while Class 2Ls are more difficult to ignite, flammable refrigerants are still flammable, and an ignition event can occur in an uncontrolled situation. The search for new refrigerants, which have desired climates and performance characteristics, will result in the use of more flammable refrigerants, primarily Class 2L and Class 3. Many hydrocarbons are used today in small charge portable systems like refrigerators and freezers. Now I will discuss flammability characteristics in more detail by describing the tests that are run to classify the various refrigerants. These include flame propagation, burning velocity, and heat of combustion. Flame propagation tests determine the lower flammability limit for the flammables and classify them either as Class 2 or Class 3. Next, if a refrigerant is known to potentially have a higher minimum ignition energy or harder to ignite, a burning velocity test is conducted to further classify the refrigerant as Class 2L. Heated combustion is also used to classify a refrigerant, but this is a calculation and is required data for other standards. Soon, lower global warming potential Class 2L refrigerants will be used commonly in the industry. While these refrigerants will be harder to ignite, they are still flammable, especially in the presence of a flame. Standard 15 2019 now includes safety requirements specific to 2L refrigerants. Chris and John will discuss those a little later. To summarize, here are excerpts from the tables in Standard 34, listing the safety classification group, OELs, refrigerant concentration limits or RCLs, and lower flammability limits or LFLs for several refrigerants. The standard also includes the OSHA toxicity code classification as well to connect each toxicity classification. Not surprising, nearly all refrigerants in the standard are neither highly toxic or toxic. As an example, let's look at the highlighted data for R134A. You can see that R134A is classified as group A1. It is a Class A because the OEL is greater than or equal to 400 parts per million. And 134A is Class 1, so it will not propagate a flame and thus has no lower flammability limit. In this case, 134A's refrigerant concentration limit is 13 pounds per 1,000 cubic feet. This RCL value is used to determine compliance with Standard 15, which we'll explain later in the program. Now let's look at a Class A2L refrigerant, like R32 for example. R32 is a Class A because its OEL is greater than or equal to 400 parts per million. But R32 is a flammable refrigerant, so the table includes a lower flammability limit, or LFL, which is 19.1 pounds per 1,000 cubic feet. The RCL for flammable refrigerants is typically defined by dividing its LFL by a safety factor of 4. So Standard 34 serves as a companion to Standard 15 in that it defines the safety group classification and provides relevant safety data for each refrigerant.
Thanks, Steve. John started us off by introducing the 3 steps for determining which safety requirements apply to a given refrigerating system. Steve just showed us the first step, identifying the refrigerant safety group classification. John, take us through the remaining steps.
Sure. As you recall, the second step is to determine the occupancy classification of the space that houses the refrigerating system. Standard 15 defines these 6 occupancy classes to reflect the various uses of a building, as well as the ability of the people inside to respond in case of an emergency. For example, the institutional classification includes facilities where occupants may have difficulty evacuating, such as hospitals, nursing homes, or prisons. As you'd expect, the refrigerant safety rules are more restrictive for these types of buildings. But industrial facilities are at the other end of the spectrum. Because access to the building by the general public is typically prohibited, the safety rules tend to be less restrictive. The third step then is to determine the system probability classification. For this step, Standard 15 classifies refrigerating systems according to the likelihood or probability that refrigerant leaked from the equipment could reach the occupants of the building. A high probability system is one in which the location of its components is such that a leak from a failed connection, seal, or component will result in refrigerant entering the occupied space. Now, some common examples include a packaged DX rooftop unit, a DX split system, water source heat pump, a VRF system, or a PTAC. Now, in contrast, a low probability system is one in which the location of its components is such that a leak cannot result in refrigerant entering an occupied space. Now, probably the most common example is a packaged water chiller located in a machinery room that delivers chilled water to remote air handling units or terminal units. Now, with the safety group, occupancy, and system probability classifications identified, let's look at how to determine which safety rules apply. Section 7 in the standard includes several restrictions on refrigerant use, which depend on the classifications we just explained. And then Section 8 prescribes installation restrictions, which are specific to the type of refrigerating system being used. In general, these rules define how much refrigerant can be used in a given application and detail any specific restrictions or design requirements that apply. And then the standard includes a list of general requirements in Section 11. These apply to any type of refrigerating system. Now, most of these general requirements are self-explanatory, so we won't talk through them today. And also, there is a Section 9 that includes requirements related to the design of the equipment itself, much of which is in the purview of the manufacturer. So we're not going to dig into that section today either. So let's go ahead and look at the restrictions in Section 7. First, the standard restricts the use of Group A3 or B3 flammable refrigerants to only a few exempt applications. Certain laboratories and industrial occupancies are exempt, as are small self-contained systems such as vending machines, refrigerators, or water coolers, as long as the refrigerant charge is very, very small. Next, the standard prohibits A2, A3, B1, B2L, B2, and B3 refrigerants from being used in a high probability system for human comfort. Now, that leaves only A1 or A2L refrigerants to be used in this application. But again, industrial occupancies are exempt, as are self-contained systems with a refrigerant charge below the stated threshold. Now, note that in Standard 15, the terms unit and self-contained are used interchangeably. They're defined as complete factory-assembled system that has no refrigerant-containing parts that need to be joined together in the field, other than by a companion or block valve. Now, as I mentioned, other than these exceptions, only A1 or A2L refrigerants are allowed for use in a high probability system for human comfort. But for A2L refrigerants, due to their flammability characteristics, the standard prescribes some extra special requirements in Section 7.6. Chris will talk through those later in the program. Now, for these high probability systems, next we'll look at Section 7.2. This is where the standard refers to the refrigerant concentration limit, or RCL, that Steve introduced earlier. It states that the concentration of refrigerant that would result from a complete discharge from an independent refrigerant circuit of a high probability system cannot exceed the RCL amount listed in Standard 34. Now, I'll come back to this, but first, note that again, self-contained systems with small refrigerant charges and certain laboratory spaces are exempt here also. And then there are these two subsections that include other exceptions. In the first, if the space is classified as an institutional occupancy, the RCL amount is actually cut in half. That is, the refrigerant concentration resulting from a discharge cannot exceed 50% of the RCL. Now recall that this category includes facilities where occupants may have difficulty evacuating, so this concentration limit is more restrictive. The other subsection addresses industrial occupancies and refrigerated rooms. These types of spaces are exempt from the RCL limit as long as they meet a list of special conditions spelled out in this particular section of the standard. So now let's go back to the refrigerant concentration limit. Now first, remember that a high probability system is one in which the location of its components is such that a leak will result in refrigerant entering an occupied space. The calculation of refrigerant concentration is based on a single event in which all the refrigerant in an independent circuit completely discharges into a space. If the resulting concentration in that space does not exceed the RCL, then the occupants should not be exposed to a harmful level of refrigerant, provided that the refrigerant disperses equally. Now, to calculate the refrigerant concentration, you divide the refrigerant charge by the volume of the occupied space. Note that the numerator is not the sum of the refrigerant charges in all refrigerating systems. Rather, it's the quantity that would completely discharge from the worst case independent circuit. So if a space houses or is served by components of more than one refrigerating system, or a system with more than one circuit, it's necessary to review each circuit separately to ensure that its combination of refrigerant type and charge meets this RCL threshold. Next, the denominator in this calculation is the volume of occupied space into which the refrigerant disperses in the event of a leak. For this, we are directed to section 7.3 in the standard. This section defines two types of occupied spaces: a non-connected space and connected spaces, which Standard 15 currently calls ventilated spaces. A non-connected space is an enclosed occupied space that contains part of a refrigerating system, but is not connected to other spaces by permanent openings or ductwork. Refrigerant released into a non-connected space essentially stays in that space and does not disperse into other parts of the building. Some examples might include a hotel guest room that includes a PTAC unit along the wall, or a classroom with a high sidewall terminal unit as part of a VRF system. In this case, the volume of this individual non-connected space is used to calculate the refrigerant concentration versus the RCL. Now, Chris will show us some examples in a bit. On the other hand, connected spaces are occupied spaces that will be affected by a refrigerant leak, where part of the refrigerating system that serves these spaces is located within an air handling unit or duct, or in an occupied space that's served by a shared mechanical ventilation system. Refrigerant released into connected spaces disperses into more than one space, as well as the air distribution system. A common example is a DX rooftop unit, where the evaporator coil is located in the airstream that supplies air to several occupied spaces in the building. Another example might be a water source heat pump or a VRF terminal installed in the ceiling plenum and connected to one or more occupied spaces by ductwork. Now, for connected spaces, the volume used in the calculation is the smallest volume into which the leaked refrigerant could disperse. So you include the volumes of all spaces that are connected via permanent openings, plus the volumes of all spaces that are served by common supply and return ductwork, including the volume of the ductwork itself, unless they can be totally closed off from the source of the refrigerant leak by something other than a smoke or fire damper. Now, the standard specifically addresses VAV boxes and clarifies that you can include the volume of the space it serves as long as the box does not close below 10% of its design airflow. And finally, you can include the volume of the ceiling plenum if it's part of the supply or return air system. Again, Chris will be showing examples for some common applications next. Now, with connected spaces, there's sometimes confusion about what constitutes a permanent opening. On the previous slide, I listed an official interpretation from the Standard 15 committee that addresses this question. Okay, so when you know the refrigerant charge and the volume of the space, you can calculate the refrigerant concentration. If that concentration exceeds the RCL threshold, then either the refrigerating system is not permitted as designed, or that space must meet all the requirements of a machinery room. Now, the term machinery room has a special meaning in Standard 15. It's defined as a space that meets specific requirements listed in Section 8 of the standard. Now, I'll explain a little bit more about machinery rooms later in this program. But next, Chris is going to walk us through a few examples to better understand the calculation of refrigerant concentration. Chris?
As John just explained, Section 7.2 says when there is a complete discharge of refrigerant into an occupied space, the refrigerant concentration must not exceed the RCL threshold. So let's step through a few examples. First, we'll start with the VRF system, looking at both a commercial and an institutional occupancy. Then we'll look at a packaged rooftop VAV system. Finally, we will review an indoor chiller installation. In this first example, a VRF system serves the ground floor of a small office building. This occupancy consists of offices, conference rooms, and other spaces. The VRF system has a single 20-ton air source outdoor unit with sealing cassettes for each zone. When we include the refrigerant piping, the total charge is 36 pounds of R410A refrigerant. It is important to note that R410A is an A1 refrigerant. As John mentioned, there are different requirements for an A2L refrigerant that I will discuss in a moment. The occupancy classification is commercial, as a refrigerant leak from one of the VRF cassettes could result in the charge entering the occupied space. It is classified a high probability system. Further, it is possible to vent the entire charge to a single zone. Therefore, we must evaluate the RCL for each space. Let's define a space. In our example, a space is any area with a cassette that is isolated with a closed door. This isolation is what defines the RCL calculation. However, spaces that are always connected by permanent fixed openings, like the reception area, the corridors, and the workspace, can be grouped together for one calculation. Then we have the closets, the elevator shaft, the mechanical room, and the storage room. These are not served by the VRF system. They do not have to be considered in the RCL calculations. Again, this will be different for A2L refrigerants. And since the vestibule and the restroom are conditioned by transfer air, we can ignore them too. So for this example, the smallest occupied space is Office 2. The volume is 2,695 cubic feet. If we discharge the entire 36 pounds of refrigerant into this space, the refrigerant concentration would be 13.4 pounds per 1,000 cubic feet. Standard 34 shows the maximum RCL is 26 pounds per 1,000 cubic feet. Since the concentration for the smallest room is less than the maximum allowed, we know that it is also less than the maximum for all larger rooms. This system is compliant with Section 7.2. For the second example, we will use the same 20-ton VRF system, but change the building to an institutional occupancy. Per the standard, institutional occupancies reduce the RCL by 50%. As John stated, this is a safety consideration, as the occupants are not able to leave without assistance or of their own free will. As we saw, the RCL for R410A is 26. For an institutional facility, it's then reduced to 13. In this example, the smallest occupied space is still 2,695 cubic feet. As we previously discussed, this results in a refrigerant concentration of 13.4. This is a problem. This exceeds the institutional RCL of 13 and does not comply with the standard. So what can we do? To lower the refrigerant concentration, you have two choices. You can either reduce the refrigerant charge or increase the space volume. As John mentioned, one way to increase the volume is to use connected spaces. If adjoining spaces are connected by permanent openings, their volumes can be combined. The standard also states that if two spaces are connected by supply and return ductwork, their volume may also be combined. So one option is, instead of using a sealing cassette as shown on the left, we could change the design on the right. This uses a ducted terminal with a sealing plenum-free return. This allows us to include the volume of the sealing plenum. This interstitial space is 1.5 feet tall. When we multiply 1.5 times the area of the floor plate, it adds an additional 8,725 cubic feet. Wow. The result is that the refrigerant concentration decreases to 3.15. This is well below 50% of the RCL, and the space complies. But we'll still need to evaluate the other spaces. We will continue to calculate the next smallest and so forth. Once a space is determined to comply without modification, then we can stop, as we know all larger spaces will also comply. Also, remember, this is just one example. There are multiple methods to increase space volume or reduce charge. Before we leave this example, I've been asked, if we exceed the occupied space RCL, Can I just install a refrigerant detector? Well, the short answer is no. Unfortunately, Standard 15 does not recognize refrigerant detectors in lieu of complying with the RCL. Where detectors are required, such as in a machinery room or when using A2L refrigerants in the occupied space, they are just one component of a multiple component compliance path. Per the standard, refrigerant detectors are never accepted as a standalone mitigation. For the third example, we'll return to the small office building. So the occupancy is again classified commercial, but this time the building is served by a rooftop VAV system. The packaged rooftop unit consists of two independent 10-ton refrigeration circuits. Each circuit contains 20 pounds of R410A. Each space is served by a VAV unit, where the VAV boxes do not close below 10%. The system also uses a ceiling plenum return. This system is categorized as a high probability system because a leak by either circuit would discharge into the supply air and then to the occupied space. In this example, the volume is the sum of all the occupied spaces. This is because they are all served by a single ducted air system, and the minimum airflow for each VAV box is set no lower than 10%. You can also add the total volume of air distribution, including the supply ductwork. However, you cannot double dip, as the volume of the ductwork is already included in the ceiling plenum calculation. We're going to exclude it. Just like in the first example, we're going to also ignore the vestibules, the closets, the elevator shafts, the restrooms, and all the other spaces that are not served by the ductwork. In this example, the total volume is 61,072 cubic feet. Next, when two circuits serve the same space, only the charge of the largest circuit is used in the RCL calculation. For this system, that's 20 pounds. If the 20 pounds is completely discharged, the resulting concentration would be 0.33. This is well below the maximum RCL and absolutely complies with Standard 15. This is also very typical of package systems. Further, even if we were to change to a ducted return instead of a free return, the system would still comply. And the reason why is because package systems serve large floor plates. This results in a greater volume for dilution. When using an A1 refrigerant, package systems rarely exceed the RCL. For our last example, we have a 600-ton chiller located in a separate mechanical space. The chiller is comprised of a single refrigeration circuit containing 1,800 pounds of Group A1 R134A refrigerant. The space volume is 32,400 cubic feet. Since the entire refrigerant system is housed indoors and a leak would be exposed to the occupants, this room could be considered a high probability occupied space. However, when we calculate the refrigerant concentration, it is 55.6. Standard 34 lists the maximum RCL for R134A as 13. This is not going to work. This requires we do something different. Where the quantity of the refrigerant exceeds the limits defined by Section 7.2 and 7.3, Standard 15 provides an alternative path in Section 7.4. This is called a machinery room. John will provide an overview of those requirements in a little bit.
Thank you, Chris. So far, we've talked about refrigerant safety group, occupancy, and system probability classifications, and how those determine Standard 15's restrictions on refrigerant use. Next, we'll overview some of the requirements that relate to a few specific applications. Chris will go first and discuss the use of A2L refrigerants in high probability systems. Chris?
As John mentioned earlier, Standard 15 prohibits the use of A2, A3, B1, B2L, B2, and B3 refrigerant from being used in high probability systems for human comfort. That limits the designer to either an A1 or an A2L refrigerant. As A2L refrigerants are low flammable, Section 7.6 prescribes additional requirements. Starting with the occupied spaces, this section clarifies these spaces must still comply with the RCL thresholds listed in section 7.2. In addition, no open flames or unclassified electrical devices are permitted in the ductwork. However, hot surfaces greater than 1290 degrees Fahrenheit, such as a duct heater, may be used when combined with both a minimum face velocity of 200 feet per minute and an airflow proving device. Next, a refrigerant detector must be installed if the space is classified residential and the largest circuit's refrigerant charge is greater than 0.212 times the refrigerant's lower flammability limit. As Steve previously stated, the lower flammability limit is also called the LFL and may be located in Standard 34. If the space is classified commercial, public assembly, or large mercantile, a detector is required when the refrigerant concentration exceeds 50% of the RCL, and if the space is institutional, a detector is always required. Finally, a detector must always be provided when it's part of the product listing. When required, this refrigerant detector must be located so that it can detect a refrigerant leak whether the system is operating or not. For refrigeration systems that are connected to the occupied space via ductwork, the detector must be in the listed equipment. However, for systems that are located in the occupied space without ductwork, the detector may be in the equipment or the occupied space. If the refrigerant detector measures a concentration greater than 25% of the LFL, the system must quickly turn off any compressors or heaters and open all dampers. It then ramps up the supply fan to the minimum airflow as prescribed in the standard. It then must remain in this mode for at least 5 minutes after the refrigerant concentration has dropped below the 25% threshold. Previously with A1 refrigerants, we ignored the unoccupied spaces. Now if an unoccupied space contains compressors or pressure vessels containing A2L refrigerant, it can exceed the RCL only if it meets all of the following requirements. First, the refrigerant charge in the largest circuit is limited to 6.6 pounds for residential or institutional occupancies, or 22 pounds for commercial, public assembly, or large mercantile. Next, a refrigerant detector must be installed in the space. And if the measured concentration exceeds 25% of the LFL, an exhaust fan must activate the prescribed minimum airflow. This airflow must be discharged outside or into a space where it will not exceed the RCL. And again, no open flame devices, unclassified electrical devices, or hot surfaces greater than 1290 degrees Fahrenheit. That's an overview, but there's more detail in the standard and in the Trane application manual that Jeanne mentioned earlier.
The other specific application we'll discuss further is machinery rooms. For larger refrigerating systems, like the water chiller in Chris's example, we saw that Section 7.4 often requires that all components containing refrigerant must be located in a machinery room or outdoors if the quantity of refrigerant exceeds the RCL threshold. Now, as I mentioned, the term machinery room in Standard 15 is defined as a space that meets specific requirements laid out in Section 8. Now, these requirements vary somewhat based on the refrigerant safety classification. For non-flammable A1 or B1 refrigerants, the machinery room must comply with the requirements included in Section 8.11. For flammable A2, B2, A3, or B3 refrigerants, the room must comply with both Section 8.11 and 8.12. And for A2L or B2L refrigerants, the room must comply with some of the requirements in Section 8.11 while also complying with Section 8.13. Now, some requirements apply to all machinery rooms, regardless of the type of refrigerant. Most of these are self-explanatory. Tight fitting, self-closing doors. Any openings to other parts of the building for pipes, conduit, or ductwork, for example, must be tightly sealed. Gasketing must be used on doors or access panels in ductwork or air handlers. and access to the room must be restricted to authorized personnel only with clear signage posted. And other requirements differ based on the refrigerant safety classification. For example, if your machinery room requires a refrigerant detector to detect if a refrigerant leak occurs, and mechanical ventilation to remove that leaked refrigerant. But the specifics vary. For all refrigerants, you need to choose a detector that's able to measure below the occupational exposure limit, or OEL, of the refrigerant being used. This detector is used to both actuate an alarm and start the alarm rate ventilation. The alarm must use both audible and visual indicators located inside the machinery room and outside each entrance. And the sampling point must be in a location where refrigerant is likely to concentrate. Now, most commonly used refrigerants are heavier than air, so oftentimes the sampling point is positioned near the floor, below the breathing zone of the occupants. If a group A2L or B2L refrigerant is used, due to its flammability, there are some additional requirements. In this case, the standard requires 2 different alarm levels, trouble and emergency, with specific set points and response times for each. In addition, if the refrigerant concentration exceeds 25% of the lower flammability limit, the detector must also de-energize compressors, refrigerant pumps and valves, and any other electrical sources of ignition. Now, moving on to the requirements for machinery room ventilation, the standard actually allows for either natural ventilation or mechanical ventilation using powered fans. Natural ventilation is allowed if the refrigerating system is sheltered by a penthouse or lean-to that's open to the outdoors and located more than 20 feet from building openings. But if the machinery room is totally sheltered from elements and not open to the outdoors, mechanical ventilation is required. And the standard requires 2 different airflow rates, normal and alarm. The first, normal ventilation rate, is required whenever the machinery room is occupied. The system must provide at least 0.5 CFM per square foot of machinery room floor area, or 20 CFM per person. Now, designers typically use the half CFM per square foot value because the number of occupants in this type of space can be difficult to predict. A secondary requirement is that sufficient ventilation must be provided to prevent the machinery room temperature from rising more than 18 degrees above the inlet air temperature, or a maximum room temperature of 122 degrees. Now, in many cases, the half CFM per square foot should more than meet this secondary requirement. But if the machinery room has a lot of heat sources, like larger air-cooled motors, it may be necessary to increase the normal ventilation rate to comply with this room temperature limit. Now, the second rate is the alarm ventilation rate. This is the rate that air must be removed from the machinery room whenever the refrigerant detector indicates the concentration has risen above the stated threshold, which is the OEL for most refrigerant safety groups. This airflow is calculated based on the mass of refrigerant in the largest circuit, and not the total amount of refrigerant in all systems located in the room. Note that the equation for calculating this alarm ventilation rate does differ based on the refrigerant safety classification. For example, for A2L or B2L refrigerants, this rate also depends on the system's operating pressure. Now, in order to provide these 2 different ventilation rates, use either multiple exhaust fans or a multi-speed fan. The standard requires that exhaust inlets be located where the refrigerant is likely to concentrate. And the air must discharge outdoors to a location that doesn't cause a nuisance or danger. It also requires provision for inlet air to replace the air being exhausted, which must be totally separate from any other building ventilation system. And the inlets for this replacement air must be located to avoid recirculation of the exhausted air. So you'll need to consider the location of the chillers and replacement air inlets when laying out the machinery room. As I mentioned, refrigerant vapor that's heavier than air will accumulate near the floor. For this reason, in this case, it's typically best to locate inlets to the exhaust ductwork below the breathing zone. And then make sure the layout provides good air movement and allows the inlet air to sweep across the refrigerating equipment before being drawn into the exhaust ductwork. Finally, account for the density of the refrigerant when sizing the motor for the exhaust fan, since higher density requires increased horsepower. Okay, let's go back to our table. If a flammable refrigerant is being used, there are additional safety requirements which don't apply to a non-flammable refrigerant. For example, the walls, floor, and ceiling of the room must be tight, non-combustible construction, and at least 1 hour fire resistive if they adjoin occupied spaces. In some cases, the room may need to conform with special requirements in the National Electrical Code. And also, the machinery room must include remote control outside its entrance for shutting down all refrigerating equipment in case of an emergency. And finally, the standard includes requirements related to the use of open flame devices or hot surfaces in the machinery room. Now, there's often some confusion about this last one, especially since chillers and boilers sometimes share the same mechanical space in a building. Again, the requirements vary based on the refrigerant safety classification. For a flammable refrigerant in group A2, B2, A3, or B3, the standard explicitly prohibits any flame-producing device or hot surface from being installed in the same machinery room. Then for non-flammable A1 or B1 refrigerants, the standard starts by saying no open flames, but then lists 2 exceptions. The first allows combustion equipment, like a boiler or a furnace, to be installed in the machinery room as long as the combustion air is ducted from outside the room and sealed to prevent any leaked refrigerant from entering the combustion chamber. Or, if that's not possible, the second exception allows you to use the refrigerant detector to automatically shut down the combustion equipment if it ever detects a refrigerant leak. So how about the lower flammability 2L refrigerants? For this safety group, the standard refers back to the same section I just showed, allowing either ducting of the combustion air or using the refrigerant detector to shut down the flame-producing device. So if only A1, B1, A2L, or B2L refrigerants are used, then a boiler can be located in the same machinery room as a refrigerating system as long as one of these exceptions is met. Now, as Jeannie mentioned, the application manual goes into more detail on each of these requirements, including the design of a machinery room.
Before we wrap up today, one other topic that comes up often is refrigerant piping. This is used to convey refrigerant from one part of a system to another. Chris, how does Standard 15 address this component of the system?
In Section 8, the standard includes several requirements related to the installation of refrigerant piping. All field-erected joints must be exposed for visual inspection prior to being covered or enclosed. If installed in concrete floors, it must be encased in a pipe duct and properly isolated to prevent damage due to vibration, corrosion, and expansion contraction. If the piping crosses an open space, it must be no less than 7.25 feet above the floor. And refrigerant piping cannot be installed in an enclosed public stairway, stair landing, or means of egress. Similarly, piping cannot be located in an elevator or dumbwaiter shaft or any shaft that has openings to living quarters or a means of egress. Unfortunately, the definition for means of egress is not universally agreed upon. So you're going to need to work with your code officials to clarify the impact. The committee understands that this lack of definition creates a burden on the designer. And as of this program, the committee is actively working to better define this section. So please, periodically check back with ASHRAE.org to see if the guidance has changed. And finally, the standard restricts pipe penetrations through floors, ceilings, and roofs, but there are several exceptions. For example, penetrations are allowed between the basement and first floor, or between the top floor and the roof or mechanical penthouse. And the standard also allows penetrations between adjacent floors if they're served by the same system. Depending on the installation, these requirements can sometimes be a challenge for systems that use interconnecting piping.
So that's our overview of ASHRAE Standard 15. We hope you enjoyed the E&L program and that you found it a helpful way to learn about the standard. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic, including the application manual we mentioned. Or contact your local account manager for specific information on Trane systems, equipment, controls, and services. And for those of you seeking continuing education credit, check out the newest online courses at trane.com just under self-paced learning. And fill out a survey to let us know what you thought of today's program. Finally, ask your local host for details about upcoming E&L programs. Thanks for joining us today. We look forward to seeing you next time.